So we have two final tests to talk about for convergence and when you do the integral test, you are comparing the results of the divergence or convergence of an integral with the convergence or diverging nature of a series. So that technically is a comparison test. And so let's count it as such. So the integral test. And that's when you compare the behavior of an integral and a series. And you probably are uncomfortable a little bit with the sketchiness of what you call sketchy, because I'm just telling you that these tests work, and I've not ever really proved to you that these tests work. That's kind of beyond what we need to do in terms of the scope. All right, the second comparison test is called direct comparison. All right, and so in this one, we're not comparing to an integral, but we compare the behavior of two comparable series, or two similar. So we're going to talk about that one today. And then the last one is the limit comparison test. Comparison. And then when direct comparison doesn't work, you compare the limit of the ratio of two similar series. All right. These are the last ones. So these are the three comparison tests. You've worked with one already, and we're going to work on the other two. All right, here is the comparison, direct comparison. So we need to think of two separate series. So given series A sub n and given series B sub n. We've talked about this when we were doing the integrals, when we were doing integrals that had bounds that approach to infinity. We sort of talked about this. So if you've got two separate series, if the A series is always less than or equal to the B, let's write it as the sum. If the sum of the A series is always less than or equal to the sum of the B series, you can do that by growth rates like n-tuple, knowing which one is larger. You can do it by just knowledge of graphs, which one is going to be exceed the other, which one's always going to be less than the other. So if you can compare them that way, then you have two cases. Then all right, B will diverge only if what is true? Okay, All right, so if B is the larger of the two, you can prove that B will diverge only if you've proved that A diverges, because you got to prove the smaller one diverges, and then you can assume, well, if the other one's bigger than this one that's smaller, and the smaller one is diverging, then the bigger one has to diverge. Otherwise, it wouldn't ever be bigger. And then we can also come up with another option for A. A sub n will converge, say this is the smaller one, only if B sub n converges. Now, what if A converges? Can we conclude anything about B?
No, B might be wild.
Okay. What if B diverges? Can we conclude anything about A? No. Which is often, you know how those multiple choice questions where they have Roman numeral 1, Roman numeral 2, which of the following might be true? And it's like 1 might be true, 2, 1 and 2, 1, 2 and 3, 1 and 3. They love that for this kind of thing. Okay, they give you 2 and they say which of the following could be true. So it can only go, you can only prove divergence for the smaller one, and you can only prove convergence for the larger one, based on how the other behavior happens. All right, so let's try a couple of these. Okay, so that's direct comparison. All right, first example. All right, so determine the behavior of going from n to 0, n is 0 to infinity of x to the 2n over n factorial squared. Right? Okay. We need to be able to compare this function to something, we don't know the convergence or divergence of this, to something we do know the convergence or divergence for. Okay, so one thing we can look at, is, well, we want to keep, I think, the numerator the same right now. So thinking about, let's just look at the denominator. Okay, x, we'll keep that the same. And Brennan is suggesting just plain x and factorial, so dropping the square. The first one, the white one in white, its denominator will be how compared to the second one? Its denominator is going to be bigger. So if its denominator is bigger, then what do you know about the terms of the one in yellow? Okay, so by making the overall, because the denominator is bigger, or the denominator is smaller, our terms will be bigger. And so we compare these two to each other. And so you're usually going to focus on your denominator. And so we know that those two will always be less than or equal to. So let's focus now on the yellow one. So we have our 2. This is our A. And then this one is our B. So let's focus on what we can prove about B. If we can prove something about B, if we can prove divergence about B, then that's no good. If we can prove convergence about B, that's where we want to go. So let's take a look at this B sequence here, series, excuse me. All right, the terms of this B sequence work out to be, if I just start plugging in 0, I'm going to get x to the 0 over 0 factorial. Then I'm going to get x to the second over 1 factorial. Then I'm going to get x to the fourth over 2 factorial. X to the sixth over 3 factorial, dot, dot, dot. We're back to, yes, I was going to say we're back to page 495 in your textbook. All right, this is the same as x squared to the 0 over 0 factorial, x squared to the first over 1 factorial, x squared to the second over 2 factorial, x squared to the third over 3 factorial, plus dot, dot, dot. So what is this the Maclaurin series for? And that's okay if you, I still have to go back and look if I don't remember, but something that has factorials in the denominator, and then, okay, it's almost e to the x. E to the x would have just been if it was x to the 0, x to the 1, x, so it's not e to the x, but it's e to the x squared. Okay, it's not e to the 2x, because then this would be 2x to the 0, 2x to the 1, 2x. This is e to the x squared. All right, so this one converges to, is less than or equal to e to the x squared. It converges to that. So if we just proved the B sequence converged, we can conclude that the A sequence must also converge because it's got to be smaller than or equal to. We do not know what it's going to converge to. Okay, that's again the big, it's not that it's going to converge to the same thing, it's just that it will also converge to something. And so therefore, the A sequence also converges, which was my original sequence. All right, let's try another one. All right, determine the convergence of n equals 0 to infinity of sine of x to the n over n factorial. So what do we want to make our B sequence be so that we can always know that it will always be bigger than the one that we have? Well, this time we want to focus on the numerator because I can't really make n factorial any smaller. N factorial is going to have to stay. But what do I know about sine, even when it's raised to an n power? It's fluctuating, right? What will it always stay either less than or equal to? Yeah, right. 1 is going to be its max, right? -1 would be its min, but we want to focus on what it's going to be less than or equal to. So we are going to assign our B sequence to be 1 over n factorial. Going from 0 to infinity. Okay, well that's going to be, if I start plugging in, I'm going to get 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, dot to dot to dot. Okay, what's the Maclaurin for that? It's good, same as last time. E to the 1, right? It's e to the numerator. And so this is e to the first, which is convergent. So then our original one, which was our A series, also converges by the direct comparison test. Since the one that's always larger converges, the one that's smaller must also converge. Okay, one more of this type. Okay. I'm going to prove this to you tomorrow, or maybe a block day. We don't need the proof, but there is a famous series called the harmonic series. It has a beautiful, gorgeous proof, which I would really like to show you. But for the sake of time, we're not going to do it today. But all right, what about these two? This is called the harmonic series. The harmonic series is 1 plus half plus a third plus a fourth plus dot, dot, dot. That's called the harmonic series. And then a similar series, 1 over n squared, which is 1 plus a fourth plus a ninth plus a 16th, etc. This one is called the harmonic series. Only this 1 over n is called the harmonic series. Okay, what do you know about 1 over n squared and why? Just not comparing to, just what do you know about 1 over n squared? The test we learned earlier. Okay, look at the power. This is the p-series test. Okay, the p-series test is the bottom one. Since p, the power, is greater than 1, what will it do? Converge. All right, so this converges by the p-series test. All right, well, what do we do with the harmonic one when the power is 1? It does not. It is divergent. It is a special series. Okay, we can't compare these two. We don't, because the first one is not smaller than the other one. The other one was bigger. And so we can't, there's no comparison we can make. So I'm telling you that the harmonic series is divergent right now. I will prove it to you on a day where we have more time. But you'll need to know what the difference between those two. So if the power is equal to 1, it's divergent. If the power is equal to something greater than 1, it will converge. All right, so that is, all right, last one, limit comparison test. And drop. Okay. Okay, in this one, given two sequences that are both always positive. In the limit comparison, we are going to do the ratio of A to B, as long as they're both positive. Doesn't work if either one of them is negative, so can't use the limit comparison test in that. So you have three options. If the limit, as n approaches infinity, if you compare A sub n to B sub n, you've got some possibilities. Well, if they're both positive and their limit turns out to also be positive, then the two series share convergent behavior. So then if you know one, you know the other. So then you look at them, okay, if I can do their ratio, okay, so let's say if I knew B but not A, and I didn't have like a comparison, I couldn't do the less than thing, I just had these two. If I knew B but not A, or if I knew A but not B, did their limit and it came out to be positive, then they will share the same convergence behavior. They'll either both be convergent or both divergent. Not one of each.
Is this excluding infinity?
Excluding infinity, no. Yes, because that's the third case. So maybe not equal to infinity. Okay, if zoom in on this a little bit more, limit of these two, when you do their ratio, I hate to say ratio because it's not the same as the ratio test, but okay, if it comes out to be equal to 0, then you have one case, and the third one is the one you're talking about, Aubrey, if the limit is equal to infinity. Okay. I'll tell you. I'm just getting. All right, there's our three cases. I don't ever have to worry about less than 0 because these were both positive to begin with, right? So I don't have to worry about less than 0. So it's either equal to 0, it's somewhere between 0 and infinity, or if it's infinity itself. Okay, if they are equal to 0, then both converge if B converges. And then if it's equal to infinity, then both diverge. If B sub n diverges. Okay, that's it. Sorry, I couldn't.